This video is intended as a walkthrough of the new procedurally drawn entity support in Interface and how to use shaders with entities to create some basic effects. Let's start off with a simple example. Here you can see three spheres. The spheres on the left and right are normal sphere entities, while the green sphere in the middle has procedurally generated color. Notice that while the non-procedural spheres are lit, the green one is not. This is because all procedurally rendered entities are treated as emissive and aren't currently included in any of the lighting calculations. Now let's take a closer look at the green sphere. If I open up the entity properties for this sphere, you'll see that the user data contains a JSON string. Because this JSON string contains a procedural entity key, and that contains a shader URL, the rendering engine knows that we want this entity rendered procedurally. In this case, I've specified a URL that points to a file on my local machine. Using a local file URL means that anyone who comes to my domain won't see the procedural surface, but will instead see a normal lit sphere. In order for others who come into your domain to see the procedural surface, you need to specify a URL that they can reach. However, using a local file URL has one advantage that's invaluable when developing your shaders, which I will get to in a moment. For now, let's open up that file and take a look inside it. This shader is pretty simple. It defines a function, getProceduralColor, which returns a vec4. This vec4 will be the color of the output pixel. Every shader that a procedural entity points to must contain this function. It is the entry point that is called by the renderer to determine the output color for a given pixel. Right now, the getProceduralColor call must return a vec4, but it ignores the alpha value. In the function, we declare a variable named color and assign it from a constant for green. We then put this into a vec4 and return it. But let's say we want the sphere to be red. I'll change the color initialization and save the file. Notice that the rendered sphere just turned red. This is the advantage of using a local file URL. The renderer keeps an eye on the file you're using and reloads the shader if the file changes. This is super handy for developing new shaders, but only works with file URLs. Let's try turning the sphere blue now. And it disappeared. So what's wrong? Well, it probably has something to do with the fact that I misspelled blue, so let's fix that quickly. The sphere is back, but let's take a look at what went wrong. If we go now and look into the log file, we'll see that it was spitting out shader compiler errors. You'll also see that it refers specifically to the misspelled name as an undefined symbol and includes the line number. This line number is important, and it's why you see the #line declaration in the shader. When it's being compiled, this shader definition will actually be part of a much larger OpenGL shader. If I didn't include that #line definition, then the line number you'd see in the log would correspond to the line within that larger shader. So if you're developing content and trying to figure out why your entity is missing or rendered incorrectly, you should keep an eye on the application log to make sure it's not generating compile errors. And including this #line definition will help you track down the location of the problem when something does go wrong. Sure, this is a trivial shader, but they can easily grow to be hundreds or thousands of lines long, so knowing the line of the compile error can be critical. Our unlit colored sphere isn't all that exciting. What can we do to spice it up a bit? In order to do anything interesting, we really need some kind of input. For our procedural shaders, there are two kinds of input. The first is uniforms. Uniforms are values provided to the shader program which are constant across every rendered pixel. The second kind are called varyings, because they vary from pixel to pixel. Don't worry if it sounds like I'm speaking Martian, I'm going to demonstrate. First, let's take a look at using a uniform. We currently have two uniforms available, a float called iGlobalTime and a vec3 called iWorldScale. iGlobalTime is the time in seconds since the shader was compiled. It's super handy for animating things, so let's try that now. Now the sphere starts out black, fades into our color, and then back out again. Although as we watch it, it seems to spend a long time in black. This is because the graph of sine goes from 1 to -1, so it spends half of the cycle with a negative color value. OpenGL will clamp color values to between 0 and 1, so anything below 0 is treated as 0, and anything above 1 is treated as 1. We can fix that by translating the sine wave up and dividing the amplitude in half. If we want it to flash faster, we can add a multiplier to I global time. Here I'm multiplying by 2 pi, so the flashing now cycles once per second. We'll demonstrate the use of the other uniform I world scale in a bit. Let's take a look at the varyings. The most important varying you'll probably use is position. This is the fragment's location in model space. The two entities we support right now are spheres and cubes. In model space, our cubes are always unit cubes, with the origin at the center, so the positions will range from -0.5 to 0.5 in every dimension. For spheres, the model space coordinates are a sphere with a radius of a half meter, so the position value will again range from -0.5 to 0.5. Here we can see the use of the position varying to color our sphere. The resulting colors aren't too bright, and there's a big dark spot. The brightness is because none of our values ever get to 1.0. We can fix that by normalizing the color vector so that it's always of length 1. The dark spot is because the values of the position are sometimes negative. We can fix that by taking the absolute value of the vector. As I said, the position values are in model space, so if I rotate the model itself, the colors rotate with it, staying on the same spot relative to the model. The sphere is now colorful, but still not very exciting. There's another tool built into our rendering system that we can use, noise functions, one each for vec2, vec3, and vec4 inputs. Each one takes a vector of the given size and returns a single floating point noise value. The functions we're providing are the simplex noise functions made available by Ashima Arts on GitHub, so if you're interested in their exact behavior, you can look at their GitHub repository, linked below. Let's try using one now by passing the position into the noise function and using the result as the intensity. This provides some variation, but not a lot, because noise functions tend to work better over a larger range of values than -0.5 to 0.5. We can increase the frequency of the noise by multiplying the position by a constant. With noise functions, you can also create a more compelling effect by iterating over the noise function several times, each time with a higher frequency but a lower amplitude, and summing the values together like so. Here, I'm using 4 passes, but I can use more to increase the perceived detail that would appear as I got closer. This is with 6 passes. Additionally, since we have a 4D noise function as well as a 3D one, we can animate the noise by using I global time as the 4th dimension passed to the noise function. Or we can combine multiple noise calls together with offsets to get a disco ball. Here we have a procedurally rendered box entity which I'm using as a floor. I've put a simple grid pattern on it to give it a nice sense of perspective. Previously, this kind of pattern would only have been possible by creating hundreds and hundreds of entities to act as grid lines and floor boxes, or by using a model mesh with a texture applied. The grid lines here are exactly 1 meter apart, but how is this possible if the position is only available in model space? This is where the other uniform, I world scale, comes in. I world scale contains the dimensions of the entity being rendered, so by multiplying it by our position vector, we get coordinates that are scaled into world space. They are not transformed in any other way, so you still don't know where in the world you're rendering or the orientation of the object, but this gives you enough information to write shaders that contain features of a fixed size, regardless of the size of the object on which you're painting them. Here, I'm multiplying the position coordinate and taking the x and z value. Since I'm using this as a floor, the box is only 1 centimeter tall, and I don't care about the y coordinate. I'm also using a combination of the OpenGL shading functions smooth step and f-width to create crisp edges around the lines nearby, while providing some anti-aliasing further away. I can also build far more complex shaders, or alternatively, I can find existing shaders and adapt them for use here. The Shader Toy website, linked below, is an invaluable source for cool effects as well as a great place to pick up techniques for use in your own shaders. For instance, this pattern is based on the Shader Toy hexagonal distance, while this one is based on the Shader Toy relentless. Once you're satisfied with your shader, you can upload it to a publicly visible location and put the web URL into the entity properties. Now anyone running the interface client who sees this entity will see it rendered using the procedural shader. Have fun and happy shading.